Welcome to another Origin seminar. Today we'll have our speaker from NOIRLab as Arvind Gupta, and he will tell us the story of searching for snapshots of giant exoplanet migrations. And the floor is yours.
Thank you. Yeah, so my name is Arvind Gupta. I'm a postdoctoral fellow at NOIRLab, where I've been for a little over a year now. For those who know me, which I see some of you in this room do, some people I didn't. Avery, when did you get to Arizona?
September.
Okay. Yeah. This isn't sort of my main science. I typically work on radial velocity studies in the extreme precision below meter per second regime. But this talk today, if you are reading the slide or if you read Allison's email with the abstract, it's on giant planet migration. So to get started, I'll start where I start with every exoplanet talk, which is the discovery of 51 Peg B almost 30 years ago now. This was not the first exoplanet ever found. That title belongs to the pair of planets found around the pulsar by Alex Volkshin and Dale Frail 3 years prior to 51 Peg B. But this one earned a Nobel Prize because it was an exoplanet found around a sun-like star. So that familiarity sort of helped propel the case for this to earn that prize. And it was very interesting. It was not only a culmination of decades of effort by people conducting radial velocity searches, which is how this was found, but also sort of a jumping off point that sort of propelled the field to be what it is today, with thousands of known exoplanets and a lot of people, a lot of work going into this science. So like I said, there are almost 6,000 known exoplanets today, although it may have surpassed 6,000 since I last checked the archive. I don't know what it's at. But I'm showing here all the planets with measured masses as a function of orbital period. And over 1,000 of these were found with the radial velocity method, just like 51 Peg B. In most of my talks, I would focus on this region. If I can get my mouse, there we go. In the bottom right over here, this is where I mostly live for my science, in the searching for Earth analogs, which of course we haven't found anything like Earth yet. This region's pretty empty. But for today's talk, we're not going to do that. We're going to stick up to the top of the plot and talk about these planets up here. So these are what we know as hot Jupiters. This is where 51 Peg B is. It was a planet with a few-day orbital period orbiting a star like the sun. It's Jupiter-sized. If we compare it to the planets in our own solar system, which I'm showing in green here, we have nothing like it, right? We have sort of this dichotomy between small planets with shorter periods and large planets with longer periods. But even those short period small planets are still, orders of magnitude longer periods than hot Jupiters. So if we go to the way we teach planet formation in Astro 101 or Planetary Science 101, we talk about the reason the large planets are farther away is because they have to form out beyond the snow line to condense volatiles, to have large Hill spheres. Planet formation doesn't work to produce these large planets at short orbital periods, or we typically wouldn't expect to do that if we're looking at our solar system-centric view of planet formation. So with 51 Peg B and these hundreds of other hot Jupiters that have been discovered, they're not intrinsically common, they're intrinsically rare, but because the detection biases favor their discovery, we know of a lot of them. That means there's a lot of research going into understanding how and why they exist where they are today. There are a few sort of classes of theories of how hot Jupiters form and exist. The first is in situ formation, where they just form where they are. This just requires, for the most part, having a higher mean mass of the extrasolar nebula so that you have enough solids and gases to form that hot Jupiter close to the star. And then the other two are disk migration, which was actually the theory first proposed for 51 Peg B very shortly after its discovery. Some folks, put together the calculations and showed that this sort of formation mechanism naturally falls out of the physics to produce a giant exoplanet if you have the right balance of competing torques from the planet interacting with the disk prior to the disk dissipating. You can have a planet migrate inwards along with that disk due to those forces. And then the other class that actually requires migration, not in situ formation, is high eccentricity migration. So here you first have some mechanism that excites the eccentricity of a initially circular cold Jupiter, So one of these mechanisms is the leadoff Kozai mechanism. If you have a stellar binary in the system, that stellar binary can torque the orbit of the planet, causing its eccentricity and inclination to oscillate over time, propelling it onto a very eccentric orbit. And then the other is planet-planet scattering. So interactions between the Jupiter-like planet and other planets in the system can kick it onto an eccentric orbit while ejecting the other planets interacting with, or just kicking that other planet onto another orbit as well. And then from here, with either of these two methods, you get to this highly eccentric orbit. And then when the planet crosses close to the host star during periastron, tidal interactions will steal energy from the orbit, cause it to shrink and circularize. And that's how we could end up with the hot Jupiters that we see today. So disk migration and high eccentricity migration can both bring us from a cold Jupiter to a hot Jupiter. And in situ formation is, for the most part, disfavored by most people today. But these other two are standing strong and alive and well in how people think about how hot Jupiters might form. For both of these, there are some observables that we might expect to see if these are the dominant hot Jupiter formation mechanisms. For high eccentricity migration, we would have to have some sort of massive outer companion that kicked it onto that eccentric orbit in the first place. We would expect the orbit to be misaligned with the stellar spin. Potentially, it's not necessarily going to happen, depending on how that excitation happened. And then we would expect to see some intermediate population of eccentric warm Jupiters, so things that haven't migrated all the way to becoming a hot Jupiter, but have gone from cold inwards somewhat and are still in the eccentric phase, but haven't quite become a hot Jupiter, or sort of fell short and didn't end up becoming one, but still maintain that high eccentricity. For disk migration, we would expect nearby companions where we wouldn't expect those for high eccentricity migration. In the sort of dynamically hotter scenario of the high eccentricity migration, we would expect nearby companions to get ejected, kicked out, thrown into the star, but those could survive with disk migration where everything moves in together. For disk migration, we expect the planetary orbits to remain aligned. There's nothing that's dynamically, again, hot that's exciting things like that. And then we'd expect any intermediate population of warm Jupiters to have circular orbits, not eccentric orbits. Again, no excitation. So there was a planet discovered in 2001, HD 806SXB. This was a planet on a highly eccentric orbit, period of 100 days or so, so a warm Jupiter, not a hot Jupiter. And it was shown through simulations that it very likely could have arrived on this orbit through a history of leadoff Kozai oscillations, because there is a stellar binary companion as well. So on the left here, this is the radial velocity orbit of the planet. You see these high excursions near periastron. And then on the right, this is these wiggles here are the leadoff Kozai oscillations, and then eventually it decouples from the perturber and is expected to circularize and become a hot Jupiter in the future. This planet was also seen to be transiting. It was discovered via the radial velocity method, just like 51 PEG-B, but it was found to be transiting as well. And what a transit allows us to do for a system like this is measure the Roster-McLaughlin effect. So this is an effect where, as a planet is transiting in front of its star, it will, if the orbit is aligned with the stellar spin, you'll first have the planet cross the blue shifted side of the star as it's rotating, and then the red shifted side. If it's misaligned, you might see something like this, where it's not, not perfectly blue then red, but still blue then red, but in a different sort of different pattern. What we expect for an aligned orbit is something like this, where if we're measuring the radial velocity of the star during the transit, we will first see that as the planet covers that blue shifted side, we'll see a redshift excursion in the radial velocity signal. Then as it covers the red shifted side during the tail end of the transit, it'll be a blue shifted excursion for the signal. But for HD 806SXB, what was observed by measuring this effect is actually a signal like this, which corresponds to an alignment that looks like this. So still mostly prograde, but not perfectly aligned with the stellar spin. Which means that 806SXB checks all three of these boxes for high eccentricity migration. It has that massive outer companion, the stellar binary that led to the leadoff Kozai oscillations. It is misaligned with the stellar spin, and it is an eccentric warm Jupiter. So this might suggest that, hey, this is how hot Jupiters form. But if you're familiar with this field, you would know that we've also seen lots of systems that are more consistent with disk migration. So these are 4 hot Jupiters shown here, the planets in red in this image. And all the gray points are nearby companions to those. And if we look at the x-axis, these are orbital periods in scales of days. So periods within a factor of 2, within a few days of the hot Jupiter, we would not expect companions like this to exist if these hot Jupiters formed via the high eccentricity mechanism. So these are very likely sourced through disk migration. And recent statistical studies as well have shown that systems like this that don't have detected companions, by analyzing the transit timing variations of hot Jupiters, show that at least 10% of them also have undetected companions like this that are perturbing the orbits and leading to these variations. So disk migration contributes to a significant number of known hot Jupiters. There have also been population level studies looking at, for example, the eccentricity distribution of warm Jupiters here discovered by TESS, and then the obliquity distribution of all exoplanets with measured obliquities. And the majority of those are giant planets because those are easier to measure the obliquities for, showing that this is not some unimodal population of planets that all have the same characteristics that might correspond to the same migration mechanism. These are multimodal. There's something more complicated going on here, and we're likely looking at multiple formation channels. But these statistical studies alone can't quite give us the answer we're looking for, because if you have this is the picture I showed earlier, right, where we have disk migration versus high eccentricity migration, trying to just distinguish between the two. If you have enough theorists invoking enough stellar physics, you can sort of make any observables correlate with any of these formation scenarios by just tweaking the physics and tweaking what the initial conditions are. So with the right environment and with the right conditions, you can produce warm Jupiters or hot Jupiters with any sorts of characteristics by either of these two mechanisms, just having variations on the two. So just looking at the observables in a statistical sense doesn't really tell you what the dominant migration mechanism is. And the case that I want to make is that in order to really understand what's going on here, we need to have more detailed case studies of individual systems like HD 80606b, where we can put together a consistent, coherent narrative about how it formed, where it got to where it is today. We know the environment, we know the initial conditions, we have a good idea of the initial conditions, and we can say very reliably which path it actually took. So we need more systems like that, where by studying those, we can learn more about the stellar physics, more about the tidal dissipation, more about the orbital dynamics than if we're just looking at things in a population sense, where that's still valuable, but that doesn't tell us the detailed information about what's actually happening in each scenario. A little bit of an aside to talk about how I'm going to get to where I'm going now. When I started my PhD at Penn State in 2018, I joined a team that was working on building this new spectrograph called NOIRLab, which a few people in here work very closely on. And this spectrograph was about a year out from being complete and sent out here to Arizona to be installed on the WIN 3.5-meter telescope at Kitt Peak. So when I got to Penn State, we were about a year out from this being complete, which was not quite enough time for me to really get my hands dirty and get up to speed on the instrumentation side of things. But it was sort of the right time for me to start thinking about the science applications of the spectrograph. This is it was designed to be an extreme precision radial velocity spectrograph. And what I mean by that is that it's supposed to be stable at below a meter per second over long timescales. You can also get single measurement precisions of below a meter per second to find low mass, long period planets. It was designed to search for, sort of work on this long-term search for long period planets like Earth. And that's a lot of what I did for my PhD. I was working on designing our long-term survey for this instrument. Now, even with a very precise instrument like this, it can get great measurements and it's incredibly stable. Radial velocity observations sort of get into this regime where we're limited not by the instrument itself, but by intrinsic stellar variability. We learned that, or we have learned over a long time, that even the quietest stars that we observe have intrinsic variations that produce spurious radial velocity signals that are at the meter per second plus level. So even with a super precise instrument, we have to figure out how to disentangle what's happening with surface granulation on stars, stellar oscillations, and signals produced by magnetic activity to try to disentangle these from the planet signals at below meter per second that we're trying to look for. So I I worked a lot on sort of this, where I conducted a case study to measure p-mode oscillations in a star and make sure we have a good handle on how those timescales and amplitudes translate to the small exoplanets we're looking for. And then I worked on an information content study to sort of study how to optimize radial velocity surveys to still detect these small signals, even in the context of the stellar variability that dominates. But my advisor, Jason Wright, was a very perceptive man. He still is a very perceptive man. And he told me that, this is really great to work on. This is sort of where the long-term future of the field and where my career should be taking me, studying stellar variability, trying to beat it down and find these low amplitude signals. But this isn't a short timescale goal. And for a PhD, you also want something that you can, observe, study, publish in the timescale of a few years and get something out to then get a job after your PhD and end up with a postdoc, which I fortunately did. But this is because he gave me really good advice. And he said I should think about some short-term science that I can do with NOIRLab. So around that same time, TESS had just launched. So for those who are unfamiliar, this is the Transiting Exoplanet Survey Satellite. For 6 years now, it has been scanning the sky one sector at a time, just like this, to monitor the brightnesses of almost all the stars in the sky and look for transiting exoplanet signals. So the main selling point of TESS relative to Kepler, which is often a comparison, is that TESS has this all-sky coverage, where Kepler just looked at one single patch of the sky continuously for several years, whereas TESS is looking at a sector at a time for about 30 days. The trade-off is that by looking at the whole sky, it has a poor time baseline, because by looking at just 30 days at a time at these sectors, there's not continuous coverage. So there is some overlap between sectors, as you can see in the orange, blue, yellow, and red here. But for most of the sky in the light blue, these are 30-day baselines. And if you're looking for a planet with a period of longer than 30 days, you won't see more than one transit. And the way that TESS, the main processing pipeline for TESS is designed, in most pipelines to look for transiting exoplanet signals, is they look for periodicities. They look for periodic signals. But what happens with these short baselines is that you don't see periodic signals. You might see a single transit for any planet with a period longer than 30 days. So I had come across this paper around the time that my advisor was giving me this advice to look for my own science, published by Stephen, Diana, and Scott, talking about how this is going to be a problem for TESS. We're going to have all of these single transit events that aren't easily detectable by pipelines. And even when they are found, they'll be really difficult to follow up because we won't know the periods of the planets. So these distributions are showing just the number of single transit candidates that we expect to find at all these periods. You see that as we get beyond 10 days, there's lots and lots of these. Again, out to longer periods, we see less because of the orbital geometry issue. So I reached out to Stephen and Diana and said, hey, you guys have this problem to solve. I have access to a new fancy spectrograph that we can use to follow up these signals. Are you interested, or what's going on? Is there something that I can do to help? And they said, hey, yeah, we are putting together a small collaboration to work on exactly this problem. So I sort of got in on the ground level there at the start of my PhD and started conducting this, campaign to use NOIRLab to follow up TESS single transits to look for long period, and by long period I mean more than 30 days, which is not actually long, but in exoplanets sometimes can be, to look for longer period planet signals. So where this ties back to what we were starting with is that lots of 30+ day signals that are seen in just one transit, you have to have a pretty high signal to noise for that transit to detect it in the first place if you have just one, which means that most of these are going to be giant exoplanets. So 30-day giant exoplanets, these are going to be lots of warm Jupiters, which can help us tell the story of hot Jupiter formation. So I set out to conduct this campaign using NOIRLab, where the sample we're selecting from is sort of large planets with 15+ day orbital periods to try to get a better handle on these warm Jupiters that are coming out of TESS. Because some of them we do see 2 transits for, we're able to get the periods, but most of them are longer and need more detailed study. And what I'm showing here in the legend is all the open circles. These are the ones where there was just one transit detected by TESS. The closed circles, there were more transits detected in future sectors, so we were actually able to constrain the period. And then these ones with the little dots trailing off the end, these were period aliases. So if TESS observes something in one sector and then again in another sector 2 years later, you see two transits, but you don't know the actual period because you're missing all of the data in between. So there's lots of possible periods that that could be correct for those planets. And just to sort of illustrate this, if we have a few sectors of data from TESS separated by 900 days, this is one planet where we're able to rule out all the short period things and some intermediate period things, but there are multiple viable aliases there still. And that's what that was illustrating on the previous slide. So for the past, or for about 4 years, I was conducting this campaign to search for these 30+ day period giant planets with NOIRLab that had been initially detected by TESS in collaboration with this group that was led by Diana Dragmir and Stephen Villanueva. The first of these I published last year. So this was one where there were some possible aliases based on the available transit data. But with NOIRLab, we were able to follow it up and figure out what the actual period was with our orbit fits. And we also got some data that was generously contributed by the SOPHIE team. And this is TOI 4127b, again, published last year. It's got a period of about 56 days and an eccentricity of about 0.75. So this is a eccentric warm Jupiter, which suggests it might align with that high eccentricity tidal migration planet formation scenario, or hot Jupiter formation scenario. But while it's highly eccentric, it's not undergoing high eccentricity migration because the period is still long enough that the tides aren't quite strong enough at periastron to cause it to circularize. If we estimate the circularization timescale based on some assumptions about the tidal dissipation parameter, which is highly uncertain, it would take much longer than the lifetime of that star. This is a G-type star that does not live for 780 billion years. But it is always possible if the tidal dissipation parameter is more efficient than we expect it could be, and this is going to be faster. But the other possibility, of course, is that the current eccentricity of this planet is not its final state. There could still be a perturber in the system, right? So we know that it had to achieve that high eccentricity by some mechanism, and there could still be a perturber in the system, or whatever perturber that got it there that's still in the system. So one of my collaborators, Jonathan Jackson, did some analysis to look at what we could and could not detect based on the available radial velocity and astrometric data, where all the black points here are what we could not detect with the available data. Blue and pink are what we could detect. We see that there's still this big parameter space of potential perturbers here that could cause it to continue undergoing eccentricity variations and end up becoming on a tidal migration track that we just simply aren't sensitive to. And these are semi-amplitudes of below 10 meters per second here, even below 3 meters per second at the bottom. So these are so there's a lot of parameter space left to be explored for this planet. And this is something that my collaborators, including John and some others, and I are very interested in following up for systems like this. We want to continue to monitor their orbits and look for potential signs of additional perturbers to see whether we can find whatever planet or star, or probably not star, but brown dwarf, caused it to arrive at this high eccentricity orbit in the first place, and whether that could be continuing to produce future eccentricity variations, and this could be a hot Jupiter progenitor. So this is sort of stuck in that stage that I was frustrated with before, where we have a lot of systems that are useful in a statistical sense, but we can't pin down exactly how they got to where they are or where they're going in the future because we don't know everything about the system. We have some inkling of what track it might be on, but we don't know enough to say for sure how it got where it is, where it's going. And I do have a few other systems that are sort of in prep, including one that's being worked on by an undergrad I'm working with, James Spall at NOIRLab, and he is getting close to getting it to publication, but I'm not going to talk about that now because he's still working on it closely. The other system I do want to talk about, though, is TSE 241249530b. Sorry, it was never a TOI, so it doesn't get a nice, easy-to-say name. You just have to memorize this number. And this one was unlike TOI 4127b, where there were multiple transits detected by TESS, TESS only saw one transit of the system. It was observed in two sectors, so sector 20 and sector 60, and just one transit was seen. See, the duration here is only about 2 hours. Now, for planets on circular orbits, there's a pretty easy way to estimate how long the transit should be based on the stellar density. You know how fast the planet's supposed to be moving around the star based on how massive the star is, how long the orbital period is. And for a planet like this with a very short transit, we would expect that the period would actually have to be very short as well, if it's on a circular orbit. But we see just one transit here, and nothing else in this whole 27-day baseline. And then in the next sector that it was observed in, we don't see any transits there as well. So we know the period is not anything shorter than 20 days or so, which is what this short duration would suggest, which means that this is probably on an eccentric orbit, unless the stellar density is very wrong, but the star is somewhat well characterized. So we know the stellar density well enough to know that it has to be an eccentric orbit, or likely is an eccentric orbit. So we started following it up with NOIRLab, and after about one season of data, one semester of data, we started to see that it, the best fit is kind of eccentric, but not going to jump to any conclusions there. So this is that initial season of data. We continue following it up. Well, we don't continue following up because there's Contreras fire, Kitt Peak shuts down. So we missed one orbit, but we keep going. It seems to still be fitting this high eccentricity curve. Keep going a little bit, and here what we did was we knew, or we suspected, we'd be approaching periastron based on what we'd seen before. So we called in some help. I put in a proposal for HPF. I reached out to some collaborators with HARPS North, and we got some extra spectrographs to try to cover that periastron passage as a hedge against NOIRLab potentially having bad weather. NOIRLab had bad weather, so this bet paid off. We got extra data, and HARPS North really kind of saved the day here and caught the high eccentricity excursion both right as the planet was approaching periastron, and then right after it passed through, sort of anchored this this high RV excursion phase of the orbit to confirm that it really is this high eccentricity. And then we kept going, got another orbit, and right here actually, these points. Oh, sorry, I thought I was going to highlight that. Sorry, we kept going, got more RV data, everything looks good. Highlighting right here, we also caught another transit from the ground. And this is another scenario where we got very lucky, actually, because we had a couple plans to try to catch that transit because we had nailed the previous periastron passage. We had a very good idea of what the period was, but again, with just one transit, there's still a lot of, several hours of uncertainty, about 12 hours of uncertainty on the transit time. So our backup plan was this telescope where we only had 4 hours. We expected the transit to actually be happening a few hours later than this, but it came in early. We got lucky. We caught the transit, and we were able to nail down the period here. But in addition to that, like I was saying, these NOIRLab data were not supposed to be in transit. Going back to this slide, we expected the transit to be a little bit later, but we ended up getting the NOIRLab data in transit, and then which. As a reminder, my slides are a little out of order. I don't have my speaker notes. We caught the transit. We were able to measure the Rossler-McLaughlin effect by having those in-transit NOIRLab RVs. We put in a proposal to get the next one as well, and NOIRLab was able to cover that. This is what we expect for aligned versus misaligned from the Rossler-McLaughlin effect, but what we saw for this system was it's actually retrograde, not just misaligned, but actually orbiting the star in the opposite direction. Again, we expect the RV excursion to go red shifted first, then blue shifted, because for an aligned orbit, we would first cover the blue shifted side of the star, then the red shifted side. But we see the exact inverse of that. With these new data, we measure the Rossler-McLaughlin signal and show that it's at least projected orbit is completely opposite the direction of the spin of the host star. So in addition, trying to check all these boxes of high eccentricity migration now, we see that the star has a binary companion, a low mass M dwarf, that through some simulations conducted by my collaborators, we show are fully consistent with a history of leadoff Kozai oscillations bringing the planet onto the eccentric orbit that we see today. So the red line here is sort of showing the present day age of the star, or estimate of the age of the star. And their simulations were showing that just like 80606b, the system would have gone through this history of leadoff Kozai oscillations before decoupling, and now arriving on this highly eccentric orbit that is causing it to circularize and become a hot Jupiter. So we have two poster children for high-eccentricity tidal migration now. 80606b discovered more than 20 years ago. Nothing since then until we found the second one, which we were able to now publish this year. Again, both of these check all those boxes. So this is a second planet for which we finally have that consistent narrative of knowing how it formed, where it's going, everything about the system and the and all the bodies that are interacting there. The other really fun thing about this, and I gave a talk about this about a year ago at NOIRLab, when this is still in progress before the paper was published. I showed this plot comparing the two systems' orbits. The first thing I want to point out is that they are surprisingly similar. They're both E of 0.93, 0.94, periods over 100 days, orbiting similar type stars. They're both late F early G stars, but then they also have similar masses. So they're both super Jupiters with masses of 4 to 5 Jupiter masses. Now, the majority of hot Jupiters have masses that are about 1 Jupiter mass or a little bit below that. They're not super high mass. They're slightly lower mass than the overall giant exoplanet population. So it was surprising to see that these two systems that are for sure hot Jupiter progenitors have very high masses. And when I gave that first talk about this, somebody asked a question saying, hey, like, are you going to look into that? Is that something you want to study? I'm like, well, I wasn't going to, but yeah, maybe I should. So the first thing was, when I was looking through the literature, there is this known trend where higher eccentricity planets have, on the whole, higher masses than lower eccentricity planets. So this is shown in some early RV search data from the late 2000s, which I guess isn't that early. That's maybe 15 years into the game. But yeah, showing that there is this known correlation between high mass and high eccentricity for giant planets. So I took a look at the whole transiting warm Jupiter population and looked at what would happen if I divided that population between high mass and low mass and fit the eccentricity distribution. Again, showing here, these are TIC 241249530b and HG 80606b on the high eccentricity end being on the high mass end as well. And by eye, you can kind of see there are more of these high mass planets at high eccentricities, and our fits show the same thing. Something important to note is that this dividing line here is arbitrary, but we test any value of it from 1 Jupiter mass to about 3 Jupiter masses, and we see the same thing. It doesn't matter where we put that dividing line. The higher mass planets have a statistically distinct eccentricity distribution from the lower mass planets, which suggests that maybe they do have different formation channels to get to these different types of warm Jupiters. And this is something that, Jian Dong and I were the two that were working very closely on this, and this is something that she is still pushing on a lot and trying to understand why, or whether there is a very good reason that there is this mass distinction. If we look at the literature, there are a few good explanations for this. So going back to this picture of high eccentricity tidal migration, these planets would start out as cold Jupiters, get kicked onto eccentric orbits, and then tidally circularize. For the leadoff Kozai mechanism that kicks these onto eccentric orbits, it turns out that we can also, at the initial eccentricity excitation, have the system be disrupted. So if that excitation causes it to be on an orbit that carries it too close to its host star, the tidal forces from the star will disrupt the planet or disrupt the orbit, strip the planet, pull it into the star, and it won't end up being, completing that hot Jupiter formation pathway, because it'll never get onto the tidal migration track. It'll just be disrupted and not be in the observed warm Jupiter population. So, and it turns out that tidal disruption distance is inversely proportional to the star to planet mass ratio. So this is showing that the fraction of systems that that gets disrupted is inversely proportional to that distance. And what this means is that the lower mass planets, the low mass planet, not low mass, but like the Jupiter mass planets that would go through Lyov-Kozai oscillations and end up in highly eccentric orbits would actually get disrupted instead of ending up as warm Jupiters or hot Jupiters. So only the very high mass planets end up as hot Jupiters because they're the only ones that can survive this part of the process. And that can explain why we only see the high mass warm Jupiters on super eccentric orbits. Anything lower mass wouldn't be observable today because it got disrupted early on. There are other explanations too as well, though. So there was a study showing that this mass eccentricity correlation could be a probe of initial disk mass. And this is looking at all giant planets detected by radial velocities. So the mass here is a little bit different, right? Because this is detected by radial velocities means we're looking at projected mass and not true mass. So there's a little bit of statistical power that needs to go into this. But the study found that there's a correlation between high eccentricity and high mass that could be traced to metallicity. Or if you have a higher metallicity system, you have a higher initial disk mass, would lead to more collisions and collisional eccentricity growth. So the high mass is a function of collisional eccentricity growth in the system, and not some other more, not a Lyov-Kozai driven thing. But this again would be a more dynamical warm Jupiter formation process and not disk migration. But even though the typical picture of disk migration keeps things at low eccentricities, there's also been a lot of work showing that you can excite eccentricities within the disk and while you're getting that disk migration. So this work here is showing that the maximum eccentricity that can be excited is actually proportional to planet mass. So higher mass planets allow you to get these higher eccentricities, which again is perfectly consistent with the distribution that we're seeing here. So the bottom line is that we are seeing this correlation between higher masses and higher eccentricities. In particular, there's this absence of low mass planets at high eccentricities. But we can't really trace that to a single formation mechanism quite yet without getting a little bit more detail about, maybe how each of these individual systems got to where they are and tracing their specific formation histories. The last thing I want to touch on today is, again, returning to this image. The one way in which these two systems differ is not an intrinsic difference between the two, but a difference in their orientation relative to us, so how we observe them. So I'm showing on the left here, this is the direction to Earth. So 80606b, it's the planetary eclipse happens close to periastron. The transit is a little bit further away, but for the one that I just published this year, it actually doesn't eclipse. The inclination is not such that it transits and eclipses, but the transit, which we do see, is right after periastron. And this can be really, really interesting for atmospheric studies. So because the transit occurs just 6 hours after periastron, this is a unique system. This is the only highly eccentric giant planet system where the transit is close to periastron phase. So with atmospheric observations of transmission spectroscopy or emission spectroscopy for the phase curve, we can actually probe the periastron phase for the first time for a system on a highly eccentric orbit like this. There have been a lot of atmospheric studies of 80606b and some other highly eccentric hot and warm Jupiters showing that the eccentricity of the system does drive some very interesting atmospheric processes, but nobody's been able to study what happens at periastron yet in transit. So we can do things like measuring the C to O ratios, refractory abundances, and sort of use those to trace the exact formation location of the system and actually fully complete the narrative from cold Jupiter to Lyov-Kozai oscillations to the warm Jupiter that we see today. And then also with those phase curve measurements, measuring both the transit and emission spectroscopy through periastron, we can look at heat redistribution, wind speeds, turbulent flows, anything else that can be triggered by this high eccentricity. So that date there, December 6th, 2025, is the only near future opportunity, I think in the next decade or so, that this can be done with JWST. So I would like to work on a proposal. If anybody on this call or in this room would like to collaborate on that, I don't have a ton of atmospheres expertise, but I'd be willing to learn and willing to help out given what I know about the system and the data I have. So yeah, if anybody wants to work on what I guess it would be cycle 5 proposal due next year. Cycle 5, please talk to me. I'd love to do this and try to get the system with JWST. I know there's also some ground-based resources we can try to get in the meantime as well. So I'll be working on that. But yeah, really interesting target for atmospheres that I hope, even if I don't get the time, I hope somebody gets the time and we can learn about what this tells us. So with that, I think I'm about out of time, so I'll leave my summary up and take questions from folks.
So for people online, if you have any questions, just raise your hand and I will call your name. And do we have any questions in the room? Okay.
Really cool talk, and I look forward to that transit. I was just wondering if the correlation you found with eccentricity and mass, if that disfavors the planet-planet scattering, because I expect the smaller planets to be more easily scattered. So would that kind of disfavor that scenario? Maybe not favor one scenario, but disfavor one?
Yeah, so that's a really interesting question, and that was my initial thought as well, right? This could not be planet-planet scattering because you expect the lower mass planets to be more easily excited, but this study right here that showed that collisional eccentricity growth is how you get these planets tells us that, yeah, I guess it disfavors planet-planet scattering as a hot Jupiter formation mechanism, but it does favor scattering as a warm Jupiter formation mechanism. Does that answer the question? So the hot Jupiters and the warm Jupiters will be formed through different pathways in this scenario.
So this particular source was initially detected in TESS.
Initially by TESS, yeah.
And you had said that for most long period planets, TESS can't really observe them. They're difficult to pull out of the pipeline because they only have one transit. So, but if you're using TESS as a source, have you developed a pipeline to find single transit candidates? How are you?
Yeah, so right. What I was saying was it's difficult for most of the pipelines that people write to find transiting signals look for periodicities. But Stephen Villanueva, who was one of the leads of the single transit group I'm working with, wrote a pipeline to search for exactly these sorts of things to key in on these single transit signals. The downside of a pipeline like that is it also produces a ton of junk. So the team, which I help with a lot of looking through junk to find these interesting things. So we do a lot of by-eye vetting of the light curves after Stephen's pipeline produces the candidates. But yeah, the pipeline exists. It just requires extra legwork on the human end as well. Yeah. Joan.
So 2 questions. One is whether the orbital distribution of the hot Jupiters, their radial separation, whether that is a constraint on the formation mechanism, because the disk, if you're going to use disk migration, it has an inner edge, and when you run out of disk, you run out of migration. So can the pileup, if there still is a pileup in the hot Jupiter population, does that say anything about favoring disk migration compared to other migration methods, which might just drive it right into the star?
Yeah, so I believe the pileup is still an observed feature. This is the 3 to 4 day pileup in the hot Jupiter population. And yeah, it naturally falls out of disk migration. But like I said, when you have enough theorists with enough physics, you can also make it fall out of high eccentricity migration. So this is, it does require a little bit more tweaking, but it is not definitively a product of disk migration. That's sort of why I think it's more important to, well, equally important to study individual systems so we can get a better tracer of how exactly they formed. Yeah.
So my second question is for Kozai, it seem to require a companion.
Yeah.
So searching for the companions might be a way to rule that in or out. Is that, how useful is that? And you kind of touched on that, but I wasn't sure whether that is just, we're not sensitive enough to test that really, or what is the situation?
Yeah, so the issue with COSI is there are systems where we see potential companions, and like the simulations show the companion could be the source. But there's a ton of systems on eccentric orbits or circular orbits where the available data aren't enough to rule out a companion in the system. Because it turns out you can have COSI with long period, you don't need a stellar companion, you can do it with a long period planet in the system too. So you just need the torque to be sufficiently strong. And a lot of these longer period planets are things that we don't have the baseline with RVs to find. Transits are pretty bad at finding the long period things, so we just don't have the data to rule them out yet. Yes.
So I've seen a similar mass eccentricity relation for directly imaged companions.
Okay.
It's a paper by Brendan Bowler showing that the higher mass brown dwarf directly imaged companions are more likely on eccentric orbits than the lower mass imaged planets. Do you think there could be a similar mechanism or mechanisms driving those trends at different mass and separation scales, but overall leading to the same?
Yeah, well, that's a good question. I feel like I've probably seen that paper. I read a lot of Brendan's work, but I didn't remember that. The different separation scales, I think, is the big key there, right? Because you wouldn't expect, if it is the same mechanism driving that and this, then it doesn't have anything to do with hot Jupiter formation. I think it probably wouldn't have anything to do with the leadoff COSI, like high eccentricity tidal migration. But it could be different mechanisms. I think if it is the same there, then it probably points towards something different that I haven't clued in on yet. But I should read that paper. Yeah. So can we do names? Gabe and
Rich Sloan.
Okay.
I had a question, just how did you know that was a real transit, those 4 points, and like not some artifact of electronic noise or something?
So I guess the big one is that through like I was saying, we do the by eye vetting of all of these signals. We get a pretty good idea of what the noise looks like, what the junk looks like. And this one didn't look like that. It looked really nice. It's looking at lots of different reductions of the test data. So we looked at not only the default pipeline, we looked, the QLP, the SPOC, Eleanor, multiple reductions of the data to make sure everything looks consistent. And it still could have been noise, I guess. But by the time we started observing it with NUID and we saw this first initial curve here, we knew we had a signal to follow up on. So there definitely have been a few that I have observed with NUID that turned out to be junk or a binary or something else we stopped observing. So yeah, we didn't know for sure. What?
I'm just disappointed to hear binaries categorized as junk.
I said junk or binaries. Junk or very different. Yeah, but I think it was mostly just getting a sense for what is and is not junk from by eye vetting. Avery.
I guess, does the fact that this source is retrograde tell you anything particular about IE migration, or is that expected to be primordial or introduced through the migration after?
Yeah, so that was actually a little contentious because I don't know if you know who Kristopol Petrovich is, but he was at Extreme Solar Systems. I was talking to him about this, and depending on how far out you expand the leadoff COSI, like if you expand it to like quadrupolar versus octupolar or whatever, you do or don't expect retrograde orbits to come out. So the fact that this is retrograde means that, whatever that corresponds to is the right amount of orbits to expand to or something. But Or it means something else happened here that was beyond the regular leadoff cosi. Yeah, so. But it is consistent with several versions of leadoff cosi simulations that you do expect retrograde orbits to fall out. Yeah. Yes, E.
Why does it take so long for you to find the second high migration planet?
Are they rare?
I don't know.
I mean, I think so, yeah. So people have done, including my collaborator, Jonathan Jackson, have done very in-depth statistical studies of the full Kepler population. And prior to the Kepler data coming out, people had done studies saying what the expected yield of these things would be. And the observed statistical studies versus expected yield show that these are way below what we expect if leadoff cosi is the full source of hot Jupiters. So a few explanations. The first is that the Kepler systems are just harder to follow up. So they're fainter, so we can't do the RVs. So there's some that are candidates for this, but haven't been able to be confirmed for this. And then with TESS, I sort of expect that we'll find more. Somebody will find more if we keep on following up systems like this. It's something that I would like to do. But the last possibility is that there is a migration mechanism where once the planet gets kicked onto the highly eccentric orbit, the migration is actually extremely fast. So they pass through this warm Jupiter phase with us having no chance of actually catching them. So they're the cold Jupiter analogs that reach a high eccentricity, and then they really quickly end up as hot Jupiters. So they're just never observable long enough for us to see them with our surveys. Yeah, it's a fast phase.
Randy, do you want to ask your question?
Yes, thank you. Really interesting talk, Arvind. I just want to make a couple of minor comments about the retrograde cases that you just alluded to a few moments ago. The retrograde cases, that obviously that has to do with the spin of the star versus the orbit obliquity of the planet's orbit. The spin of the star has very little angular momentum relative to the orbital angular momentum generally, unless it's a really, really close, particularly close or short period orbit. Stellar spin angular momentum is really small. And so that can be, tweaked, wiggled through many processes. So whether something is retrograde and you have to account for it through high eccentricity migration or scattering, I think is kind of up in the air, how important a problem that is. But getting that out of the leadoff cosi is not that hard if you put in a little bit of eccentricity on the perturber, your third body perturber. Then you can get these orbit flips. You're probably aware of that. So those are actually relatively easy. The timescales are also astronomically not crazy. So I think that could be a fairly easy explanation for so-called retrograde cases. And a pedagogical point I wanted to make was that leadoff cosi, I think the terminology or the nomenclature, there's an update to that, and you may or may not be aware of that. It's called the von Zeipel leadoff cosi. I can give you some references to that because the leadoff cosi mechanism actually was discovered, as far as we know, by von Zeipel more than 100 years ago. And it was forgotten by astronomers, and even leadoff and cosi, when they wrote their papers, were not aware of that work. And von Zeipel had done this even better to a much higher, I'd say, level of mathematical rigor than leadoff and cosi did. So I'd encourage you to call it the von Zeipel leadoff cosi oscillation.
Yeah, that's my apologies for omitting that his contributions, because I did in the paper we do of course cite all three of the von Zeipel leadoff and cosi and refer to it as that throughout the paper, but I do often slip up and omit that one when giving talks. So I apologize for that. And thank you for clarifying the orbit flip thing in more eloquently than I'm able to, because this is not, that specifically is not my area of expertise.
Well, no apologies necessary. You know, one Zipel lead-off cosi is quite a mouthful. So I abbreviate it as EZLK.
Yes.
That's easier.
So we still have time for another question. We have other questions online or in this room? No, we thank speaker again.